everyone. We are going to cover the last part of the qualitative analysis of Chapter 5 PN homojunction, which is the currents in PN junction. To recap, we have learned about the three Venn diagrams for PN junction under three different conditions, which are the equilibrium, forward and reverse bias. The main differences are as shown here. Mostly, we focus on the potential barrier or the junction voltage, the junction width, and electric field. Under the reverse bias, the potential barrier, electric field, and junction width all increase, and under forward bias all decreases. For this video, we are going to discuss qualitatively on the current flow in a PN junction under those three conditions. And then we try to relate the conditions to the current voltage characteristics of a diode. First, we discuss the current flow under equilibrium. At a glance, there are four types of current flow through a PN junction at equilibrium: the diffusion current, drift current, generation current, and recombination current. Each of the current can be further divided into electron and hole current. And for example, diffusion current is a combination of electron diffusion current and hole diffusion current. The direction of all currents are shown in the left figure. We take a look at the diffusion and drift currents at equilibrium. We have discussed multiple times on the diffusion of electrons and holes from high concentration region to low concentration region. These carrier movements will produce electron diffusion current from P to N and holes diffusion current also from P to N, which in total generated a diffusion current from P to N. Separation of charge due to the carrier diffusion will generate an electric field from N to P, which in turn induced drift currents for electrons and holes from N to P, or a total drift current from N to P. You can notice that both diffusion and drift currents cancel each other because they are flowing to the opposite directions, and the total current at equilibrium is zero. On top of diffusion and drift currents that we are familiar with, there are generation and recombination currents in the PN junction. These currents are at the transition region. I hope you still remember that generation is the process that we call the excitation of electrons from valence band to conduction band and produce electron and hole pairs. In PN junction, the electrons at P side near the transition region may be excited, and since there is an electric field, the excited electrons are being swept away out of the transition region to the N side. As a result, an electron generation current from N side to P side exists. At the same time, the generated holes are being swept away to the P side due to the electric field, which also produced hole generation current from N to P. Thus, a total of generation current from N to P exists. Electrons at the conduction band at N side may fall to the valence band, which is the recombination process. During the recombination process that happens at the transition region, recombination current from P to N will be generated. Thus, we will have generation current from N to P and recombination current from P to N that cancels out each other, and thus at equilibrium the total generation and recombination currents are zero. So this is the summary of currents in PN junction at equilibrium. Electrons and holes diffusion produce diffusion current from P side to N side. Electric field at the transition region produce drift current from N side to P side. Generation current exists from N side to P side, and recombination current exists from P side to N side. Thus, the total net current at equilibrium is zero. Now let's move on to reverse bias. This figure shows the differences of PN junction Venn diagram at equilibrium and under reverse bias. Notice the major difference of the potential barrier in the two Venn diagrams. Under reverse bias, the N side moves downwards and P side moves upward, stretching the Venn diagram and increasing the potential barrier and also increasing the electric field. Under reverse bias, since the electric field becomes larger and potential barrier becomes higher, the electrons from the N side that try to diffuse to the P side cannot cross over due to the potential barrier height, and at the same time they are turned back by the electric field. Holes also face similar difficulties to diffuse from P side to N side. Thus, diffusion currents and reverse bias are very small, that they are negligible. But at the same time, small number of electrons at the conduction band of P side may be able to diffuse to the N side due to being swept over by the electric field. Same case with the holes at the valence band on N side. This will produce what we call minority diffusion current because the carriers are minority carriers, which is also a small current. Generation also happens under reverse bias. Electrons from the valence band in P side generated and swept to N side, which will produce generation current from N to P. Recombination only happens in a very small number, thus recombination current can be neglected. When the reverse bias is further increased or made more negative, the band diagram will stretch further. At some point, electrons at the valence band of P side can tunnel through the transition region directly to the conduction band of N side. This produces tunneling current from N to P. This tunneling current increases as more negative bias is applied, because more negative bias means that the band diagram is more stretched and thus more electrons can tunnel through from P side valence band to N side conduction band. Under highly reverse bias, diodes can break down. It does not mean that the device physically breaks down, but it means that the current voltage curve does not obey the theoretical curve. Two mechanisms that can cause the breakdown are tunneling, as we have discussed just now, and also carrier multiplication and avalanche. Carrier multiplication happens when the reverse bias is very large, thus producing a strong electric field. When an electron is thermally generated in P side near the transition region, it will be accelerated to the N side by the electric field. The kinetic energy experienced by this electron is larger than the band gap, that it collides with another electron in valence band, and that second electron is generated to the conduction band. This is called impact ionization. If the second electron has enough energy to induce impact ionization, more electron and hole pairs are being created, and this will increase the reverse bias current. If the electric field is large enough, more and more collisions and impact ionization happen, and a lot of electrons and hole pairs are created. That will create a large current under reverse bias. This phenomena is called avalanche. Thus, the total current under the reverse bias are as follows. At small reverse bias, although there are small minority carrier diffusion current and small generation currents, the values are too small that there is almost no current flow. Thus, at the IV characteristic here, the current is 0. Until at some point when the electrons from P side valence band start to tunnel to the conduction band in N side, producing tunneling current. The tunneling current increases as the reverse bias becomes more negative. Another current that may also produce is multiplication current, and if multiplication is large enough, avalanche will happen. Tunneling current and multiplication current contributes to the breakdown of the diode. Next, we discuss on the forward bias. When the PN junction is forwardly biased, the N side move upwards and P side move downwards. This will decrease the potential barrier at the junction. When the barrier decreases, a large number of electrons diffuse from N side to P side, and holes diffuse from P side to N side, which will produce a large diffusion current from P side to N side. At the same time, when the junction is under forward bias, the electric field is decreased, which in turn will decrease the drift current. But the reduction of drift current is compensated by the large diffusion current. Since there are a lot of carriers that cross over the transition region, we need to consider what happens to the diffuse carriers. The electrons from N side, when they arrive at the P side, they become the minority carriers, because minority carriers at P type is holes. Similarly, holes arriving at the N side will be the minority carriers. We call these carriers as excess carriers. I hope you still remember in chapter 3, we talked about minority carrier lifetime and length. That concept is used here where the minority carriers will move and recombine as they move further into the material, meaning that when electrons from N site arrive at P site, they will start to recombine as they move more to the right into the neutral region of P type. Holes arriving at the N site will be filled up by the recombination as they move further to the left into the neutral region of N type. As the position moves further into the neutral region, the number of excess carriers will decrease until it reaches its equilibrium. Since many electrons and holes crossing through the depletion region, the opportunities to recombine are plentiful. The recombination that happens in the transition region and near the junction will produce recombination current from P to N. Unlike reverse bias, carrier tunneling is not possible. Under reverse bias, there are empty states at N site for electrons from P to occupy when they tunnel. But under forward bias, the electrons, if they try to tunnel, they will end up in the band gap with no empty states and they will be swept out by the electric field. So in total, when the potential barrier is reduced by the forward bias, a large number of carriers will cross the transition region and produce a large diffusion current from P to N. Due to the large number of electrons and holes exist in the transition region, recombination happens and produce recombination current, which is also from P to N. This will total up to be the current in forward bias, which will increase exponentially as the bias voltage increase. In summary, we have discussed on the currents for the three conditions of p-n junction. At equilibrium, where there is no applied bias or VA equals to 0, the net current is 0. When the p-n junction is biased with positive voltage, since the potential barrier is reduced, currents will increase exponentially due to the diffusion and recombination currents. When the p-n junction is biased with negative voltage, at small value, almost no current flow due to the high potential barrier. However, when the bias is made more negative, carrier tunneling and multiplication will happen and produce leakage current. So that's all for now. Please don't hesitate to ask more questions. Thank you.